Have you ever looked at two airplanes taking off from the same runway and noticed how different their engines look? One might have sleek, compact turbines, while another has enormous fans encased in massive nacelles. And you might wonder, why do commercial airplanes and jets have different engines? Isn't it all just about going fast? Today, we're going to explore the incredible world of aircraft engines, from propellers to high-bypass turbofans, and uncover why engineers design engines so differently depending on the type of airplane, the mission, and the physics involved. By the end of this, you'll never see a jet engine the same way again. To understand the answer, we need to start with a simple principle. An engine is a tool designed for a specific job. Not all airplanes fly the same distance, at the same speed, or with the same payload. A regional turboprop flying short hops between small airports has very different requirements than a Boeing 777 crossing the Atlantic fully loaded. Short flights need engines that are lightweight, responsive, and efficient at lower speeds and altitudes. Long-haul flights require engines capable of enormous thrust, optimized for high-speed cruise, quiet operation, and fuel efficiency over thousands of kilometers. The type of engine chosen is a reflection of the mission profile of the aircraft. Let's start with the main categories of engines used in commercial aviation. Most commercial aircraft use either turboprops or turbofans, while some smaller jets and military trainers use low-bypass turbofans or historically turbojets. Each has advantages and disadvantages depending on speed, altitude, and efficiency. The turboprops are essentially gas turbines connected to a propeller. They excel at low-speed, low-altitude operations. The propeller generates thrust by moving a large mass of air at relatively low velocity. This is extremely efficient at speeds below 500 kilometers per hour and altitudes below 25,000 feet. Turboprops are often seen on regional aircraft, short runway airports, and commuter planes. They consume less fuel per kilometer on short flights compared to pure jet engines and can operate on runways where jets might struggle due to takeoff length requirements. The trade-off is speed. Propellers hit physical limits due to tip speeds approaching the speed of sound, which causes drag, vibration, and noise. That's why you'll never see a turboprop efficiently cruising at 900 kilometers per hour at 35,000 feet. Turbofans, particularly high-bypass turbofans, dominate modern commercial aviation for medium and long-haul flights. In a high-bypass turbofan, most of the air bypasses the engine core and is accelerated by a massive fan. This bypass air produces the majority of the thrust, and it does so efficiently and quietly. High-bypass turbofans allow aircraft like the Boeing 747, Airbus A380, or Boeing 777 to cruise at high speeds, around 900 kilometers per hour, at 35,000 feet, while consuming fuel efficiently and keeping noise levels manageable. The engine fan may be several meters in diameter, and the nacelle enclosing it is enormous, but this is necessary to move a massive volume of air at moderate speed. The result is thrust without extreme noise and fuel consumption, which is ideal for carrying hundreds of passengers thousands of kilometers. Then there are low-bypass turbofans and turbojets, typically found on smaller business jets, private jets, or military aircraft. These engines are designed to produce high thrust relative to their size, with less concern for noise or extreme fuel efficiency. Low-bypass turbofans accelerate a smaller mass of air at higher speed, producing more thrust per kilogram of engine weight. Turbojets, now largely obsolete in commercial aviation, function similarly but without a fan, compressing air, burning fuel, and expelling exhaust at extremely high velocity. These engines excel at high-speed performance and high-altitude operation, but they're loud and inefficient at low speeds. That's why you'll see them on fast, lightweight jets rather than wide-body airliners. Noise is a crucial factor in engine selection. Airports impose strict noise limits, especially near urban areas. High-bypass turbofans generate lower exhaust velocities and move more air at slower speeds. drastically reducing noise compared to turbojets or low-bypass engines. Passenger comfort is also improved. Modern turbofans are remarkably quiet inside the cabin, whereas older engines produce significant vibration and noise. Environmental regulations and noise reduction are therefore major reasons why commercial airliners favor high-bypass designs. Fuel efficiency is another key factor. A large airliner burns enormous quantities of fuel. The difference between a high-bypass turbofan and a turbojet isn't just noise, it's efficiency. High-bypass engines are optimized for cruising at high altitude, where air is thinner and drag is lower. They consume less fuel per kilometer traveled, a critical factor for airlines that need to operate profitably over long-haul flights. Turbojets or low-bypass engines, while lighter and more compact, would consume far more fuel under the same conditions, making them economically unviable for large passenger planes. Another consideration is weight and wing design. Turboprops are lighter and can be mounted directly on wings without enormous pylons. The propellers themselves provide some lift due to airflow over the wing, which is beneficial at low speeds. High-bypass turbofans, by contrast, are heavy and produce immense thrust. They require reinforced pylons and wing structures to bear their weight and vibration. The wings themselves are designed to carry the engine mass and the aerodynamic loads generated at high speeds, demonstrating how engine type influences the entire aircraft design. Reliability and maintenance cycles are also critical. Airlines demand engines that can operate for tens of thousands of hours between major overhauls. High-bypass turbofans, with their slow-moving fans and advanced materials, provide both reliability and efficiency. Turbojets, with higher operating temperatures and faster-moving components, require more frequent maintenance and consume more fuel per distance. Maintenance considerations, therefore, influence the choice of engine for commercial operations. Historically, the evolution of engines also shaped their selection. In the early days of jet aviation, turbojets were common because they offered unprecedented speed for their time. However, as passenger comfort, noise, and efficiency became priorities, engineers developed turbofans, increasing bypass ratios to move more air at lower speed. Turboprops persisted for regional operations because they are so efficient at lower altitudes and speeds, making them ideal for commuter flights and shorter runways. Modern aircraft are the culmination of decades of optimization, balancing thrust, weight, fuel efficiency, and noise. So why do commercial airplanes and jets have different engines? It all comes down to mission, speed, altitude, efficiency, noise, and operational constraints. Turboprops dominate short, low-speed regional flights. High-bypass turbofans power large, long-haul airliners. Low-bypass turbofans and turbojets excel in compact, high-performance aircraft. Every engine is a carefully engineered solution, optimized for the physics of flight and the practical requirements of the aircraft's mission. Next time you see a regional propeller plane and a massive jetliner sharing the same runway, take a closer look at the engines. One moves a giant mass of air quietly and efficiently. The other accelerates a smaller mass at high velocity for speed and performance. Both are masterpieces of engineering, each perfectly tuned to its purpose. And that, in the end, is the beauty of aviation. No two airplanes fly the same way, and no two engines are designed for the same sky.